Okay, so here's our lesson on 1-3 linear functions, transforming linear functions, and solving problems involving them. This should actually say lesson 1-1. Excuse me. We learned to do it by point, but now we're going to use function notation and actual equations to create transformations. Alright, so a horizontal shift is where we take x minus h, meaning that h is our horizontal shift. So that what they're doing is they're kind of saying x minus h is equal to 0, and then they're solving for x equals h. So this distance here, let me see if I can do this. This distance here to here is h units long, and we moved to the right because of the minus. Whereas if we had let's say f of x plus h, we would have moved left h units. Comparatively, we notice that in this problem here, they've got f of x by itself, so it's creating the shape. And this k is just adjusting the y variable. And so whatever k is, it does. So in this case we're adding k, and so we're going to move k units up. But if we had done f of x minus k, then we would have gone down k units. Okay, here we're reflecting across the y-axis, so we need to affect the x variable by making it negative. So it's gonna mirror horizontally, meaning this point moves over here, and this point moves over here. And conversely, if we want everything to move from, say, the bottom to the top, or from the top to the bottom, we need to affect the y variable, or the entire function, f of x. So here we're going to multiply -1 times the entire function. And here's a little helpful hint. If you're adding to the y, meaning the entire function, you go high. If you're adding just to the x, you go left. So f of x plus h, we go left h units. If we have f of x, then you go high. Alright, so here we've got a function, and what they're doing is they're saying this was our original. And unfortunately, with my kind of screencasting here, I can't really have this go slide by slide, but essentially they're saying translate this function 3 units to the right until it becomes g of x, a new function that's been translated 3 units to the right. So instead of this x variable, now we're going to use x minus 3, where 3 is our h. So 3 equals h, and 3 is positive, so I know I need to subtract it from the x. All right. And then we go ahead and rewrite the function. So instead of f of x plus 3, we now have x minus 3 minus 2, because this was x minus 2, now it's x minus 3 minus 2. Alright, and then when we simplify, we end up with x minus 5. So this should, I don't know why it did that, but x minus 5. And so we see that here we've gone from an x minus 2 to an x minus 5, and so all of these points have moved 3 units to the right. Every point is translated in this function. Okay, we can use tables, and they say that this is our f of x, and we want to transform it using a new rule. So first thing we need to do is figure out what function this actually is. So I notice that I have 0, 1 as a point. Okay, well if I have 0, 1 as a point, then I know that that's also my y-intercept. And then I have an x and a y, and I can create slope. So we have m equals 2 minus, minus 1 over 2 minus 0. So I get 1 over 2. So there's our slope. Here's our y-intercept. We have y equals 1/2 x plus 1. So we have our linear function defined by the table, and they want to mirror it across the x-axis. So if I want to mirror across the x-axis, I need to affect the whole function. I need to affect the y. So right now we're saying that f of x is equal to 1/2 x plus 1. But I need negative f of x. I need to mirror across the x-axis. So I need to take negative times 1/2 x plus 1. So that I get g of x then. Because we're saying that negative f of x is going to be equal to g of x. So then g of x equals negative 1/2 x minus 1. And they've kind of done that for us. And then, again, we multiply by the negative. And here's our image. So what we originally had was this line here, 1/2 x plus 1, and then it was mirrored about the x-axis. So this point here would have gone up here. This point over here would have come down here. These points would have come down, down, down. You'll notice I'm moving from top to bottom, or bottom to top. These ones go down, these ones go up. And that means that all of these points are moving in the vertical, which is why you had to affect the entire function. You had to affect the output, not the input. Alright, so if we have this function f of x equals 3x plus 1, we want to translate it 2 units right. Well then, instead of f of x, we're going to have f of x minus 2. That's going to be equal to your new function, g of x, a translated function. So g of x equals 3 times x minus 2 plus 1. Instead of 3 times x plus 1, we now have 3 times the quantity of x minus 2 plus 1. And then we simplify and get our new function, 3x minus 5. And again, we look and notice we went from 3x plus 2 to 3x minus 5. So everything would have moved all the way over. All the way over. Okay? Alright, so we've got this function here, and we need to figure out what it is first. So again, we're going to say, well, if x is 0 and y is 2, then 0, 2 is our y-intercept. And we're going to say this is linear, so we're working with slope again. So our slope here is 3 minus 2 over 1 minus 0, which is 1 over 1. So I can write f of x as equal to x plus 2. And then they want us to transform f of x according to make g of x. And linear function defined in the table, we want to reflect across the x-axis. So again, we're going to move vertically. So negative f of x will then be g of x. So that's going to equal negative x plus 2. So then g of x should equal negative x minus 2. So we found in this slide they find f of x. You can see they use the same points I did, slope-intercept form, and then we plug in our slope of 1, so 1x plus 2 to get our new function f of x equals x plus 2. Now that we know that we're going to need negative f of x, and so we put in the negative f of x, and then we multiply the negative 1 by the entire function. They have a little typo here. This should be a plus, and then when it distributes it becomes negative x minus 2, just like I had before. Okay? And there's your two new functions. So we have x plus 2 and negative x minus 2. So these points here would have mirrored across the x-axis right here. So this is our mirror point. Imagine a mirror right here looking at the reflection of our original function. So this point mirrors over here, over here, over here. This point then mirrors here. This point mirrors across there, and this point mirrors across there all the way through. And these points are coming down, while these points are going up. Okay. As it says here, stretches and compressions change the slope of a linear function. If the line becomes steeper, the function has been stretched vertically or compressed horizontally. They look the same. If the line becomes flatter, the function has been compressed vertically or stretched horizontally. They're going to look the same. So in order to do a horizontal stretch or compression, okay, then you need to change the input. Horizontal, input. Vertical, output. So for vertical, we're going to change the coefficient of our function, whereas for horizontal, we're going to change the input value, the x value here. So if b is greater than 1, then we're going to pull away from the y value. Another way to describe pull from the y value is that it's going to get flatter. It's going to get flatter as we pull. But if we compress towards the y-axis, then it's going to get steeper. Okay, so if you're compressing horizontally, steeper. If you're stretching horizontally, flatter. Whereas the reverse is true here. If we have larger a values, then we're going to get steeper. If we have smaller a values that are being multiplied by our whole function, then we get flatter. Good hint. Your y-intercepts don't change in horizontal stretch or compression, and your x-intercepts won't change in vertical. Okay, so we have to carefully read compression here. We're compressing horizontally by a factor of 1/2, which means we're really going to get f of 1 over 1/2 x. We're not just multiplying by the input now, we are compressing. So that means that if we're compressing, we're 1 over b, where our factor is 1/2. So b equals 1/2. And so what we've got here is 1 over b times x is going to equal our new function. Well, b is 1/2, so 1 over 1/2 is the same thing as f of 2x, which is going to be g of x. So then we would say, all right, negative, instead of the x that's here, we've got negative 2x plus 4. So we've really got negative 2x plus 4 is our new function. And we see that we were right, negative 1 over b, because b is that compression factor, okay, is the factor they say. They said 1/2, so 1/2. If we had been stretching horizontally, we would have just said 1/2 was the whole thing. It'd be b over 1. Then we plug in what it simplifies to. 1/2 in the denominator becomes 2, so you get negative 2x plus 4. And that's what it looks like. Our original graph in red, or in blue here, okay, was a little flatter, and we compressed horizontally. We compressed horizontally. So our y-intercept didn't change. We're still going through 4. We're just steeper now. Okay. Okay, in this problem here, we're doing a vertical compression this time instead of horizontal. So make sure you're reading this carefully, because you may confuse yourself. So with a vertical compression, okay, we are pushing from the top and the bottom, so a steep line is going to become a flat line. We're pushing down on it. Alright, so we're going to affect the entire function now. F of x, in order to become g of x, needs 1/4 times f of x is going to equal g of x. That's our rule for g of x that they asked for. And then we'll graph. Okay, so if I do that, I got 1/4 times our entire function, 3x plus 2. Well, if I distribute the 1/4 to the 3x, I get 3/4 x. And then if I distribute the 1/4 to the 2, I get 1/2. And away we go. Alright, just for reference, our a value for vertical compression, we just take that guy, the 1/4 they gave us, and multiply it by our new function. So g of x equals 3/4 x. And here's our image. Again, our x-intercept didn't change whatsoever, but our y-intercepts did. We had this as our original, and our new right there. These should change. These should be, red should be blue, and blue should be red. So this should be g of x, and this should be f of x. Alright? So this was our original, and it got compressed vertically, so pushed down and pushed up. It's like we had a wall here, and we're pushing in this direction, flattening it out. Occasionally you may have to involve more than one transformation. So you do one at a time in the order they're given. Okay? For multiple transformations, you create a temporary function such as h of x. Remember, this is all just names. These are just labels that we are giving them. We tend to use f and g, but realistically you use whatever you need. Okay, so we're going to move on to one. We're going to represent the first transformation and then transform it to make a combined transformation. Kind of like what we did in class the other day, where we had the w that we mirrored and dropped by a unit. But with linear functions, it's really important that they go in the order they're read. Okay, so g of x is the horizontal shift of f of x. G of x, horizontal shift of f of x equals 3x. Left 6 units, so that means we're adding 6 to it. And so our temporary function, they're using h of x. Okay? And then after that, you're going to stretch it horizontally by a factor of 4. We're stretching it horizontally, so that's the 1 over b. Okay, so our first situation here is a temporary function of 3x plus 16. That's where we moved everything to the right, or excuse me, to the left 6 units. So 3x plus 18. But now we want b. We're going by a factor of 4. So we have 1 over b. 3 times 1 over b is 3 times a fourth x, or 3/4 x equals 18. So we're horizontally stretching these things. And so if you look at the original shape, we've got like x, 3x goes right here, up 3 over 1. Okay, well now we've got 3/4 x plus 18, and so it's going to look more like something like that, way up at the top. Okay. Alright, so in this example, g of x is a vertical compression of f of x equals x by a factor of 1/2, followed by a horizontal shift, 8 units left. write the rule for g of x. So they're going to perform the translation first, and then move on from there. So our translation means x plus 8. So instead of f of x equals x, we have f of x plus 8, where h of x now equals f of x plus 8. So x plus 8 is our new guy. And then we're going to stretch by a factor of 1/2. So we multiply by 1/2 the whole equation, this new h of x. H of x is right here, so let's write that down. This used to be h of x, and then this is g of x that we're finding. So 1/2 times x plus 8 should end up with 1/2 x plus 4. And then if we were to compare the two, let me draw something here. So f of x equals x looks like this. Okay, but 1/2 x plus 4 up 1 over 2, looks like that. So we had, and then h of x looks like this. 1, 2, 3, 4, 5, 6, 7, 8, and up 1 over 1. So we had g of x first, here, or f of x first rather, then h of x, and then g of x, our final. Okay? We moved 8 left, and then we compressed vertically. Alright, this is a cool problem. In this problem, we have a golf team selling t-shirts as a fundraiser. The function r of n is equal to 7.5n, represents the team's revenue in dollars, and n is the number of t-shirts sold. So how much do you think each t-shirt's worth then? If n is each t-shirt, and this is their revenue they get from selling t-shirts, my best guess is that $7.50 is what it costs for a t-shirt. They paid $60 for the t-shirts. Write a new function for the team's profit. Well, if this is revenue, your initial cost will become a starter cost no matter how many t-shirts you're sold. So if n is 0, then you've got negative 60 in the bank. And so 7.5n minus 60. This would be called a vertical translation down 60 units, or $60. Alright, so we have r if there's no cost, and n, and p if there is a cost. So they have different y-intercepts and different x-intercepts. So the profit, our profit can be negative, but you really can't ever have negative t-shirts sold. So you're always kind of starting here and working your way towards that. So in terms of how many t-shirts you sell, you'll never have a negative t-shirt, right? Okay, the graph indicates that P of n is a translation for R of n because 60 was subtracted. This indicates up. This is what I was saying earlier, vertical shift, 60 units down, and that often happens with problems like these. Okay, we have a similar problem here where we have a function R of n equals 12.5n for clubs that are selling beaded purses. They paid $75 for the materials, so we need to adjust. So in our new function then, we're going to have R of n equals 12.5n minus 75. So that's the function right there. But what if the club members decide to double the price of each purse? Well, then we have this new function here. What they really did was they said, okay, let's take R of 2n equals 12.5 times 2n minus 75 to get 25n minus 75. Okay? And here we have our two lines. Okay? Obviously the profit goes up significantly if we double our cost, assuming that the same number of purses are sold in either case. But just from an economic standpoint, demand's going to go down for something like that as soon as the price goes up. So you may not necessarily make more money just because you double your price. So again, we compressed horizontally because we got steeper here, but we also had a translation down 75 units. Right? So our compression factor was actually 1/2 because we went twice as steep. And then we're only saying that because it's horizontal compression. So if we're compressing this way, okay, then we have to think, all right, if this is 2, well then 1 over whatever this is our factor that compresses like this. If this number got smaller here, well then this number would probably be larger. Alright, so these are a few that you can try on your own, some quick ones with 3x plus 1. So if you have a horizontal translation 3 inches to the right, you're going to plug in 3 times the quantity of x minus 3. So then you get 3x minus 9 plus 1 is 3x minus 8. If you're reflecting across the x-axis, you're going to affect the y value. So you're going to take -1 times 3x and -1 times 1 here to get -3x minus 1. And then our vertical stretch by a factor of 2. So I'm going to multiply the entire equation by 2 because it's vertical stretch. So we keep the factor whole. If it was horizontal stretch, we would go 1 over. So vertical shift up 4 units followed by a horizontal compression of 1/3. So a compression of 1/3 means 1 over a third. And so we need to shift up 5 units, or up to plus 5. But then we also need to say 3 times 3x to get 9x plus 5. Alright? Alright, and here is a little quiz for you to try, and here's the answer. So the cost of a classified is represented by 150L plus $4, where L is the number of lines in the ad. So it's $1.50 a line with a minimum cost of $4. The cost is increased by $3 when color is used. So we want to write a new function for the cost of the classified ad in color and describe the transformation. So all they're saying is that the starting cost goes up by a total of $3, not $3 per line, not any of that. That means that this is like our base price originally, and now this plus that become our base price for $7. Still $1.50 a line, that never changed. It just means that no matter what, you're paying at least $7. And realistically, you're really paying, well, a reasonable minimum price for each of these would be $5.50 or $8.50. Now, why do you think? Well, hopefully you're saying to yourself, why would I ever pay $7 to somebody to create a 0-line ad? Why would I ever do that? Okay? So maybe write a little, blurb about why would I ever create a 0-line ad where I don't put any text or nothing in it. I would never do that. So you at least have to have 1, making it 150 plus 7 and 150 plus 4. Okay, I hope this helped.